The DT5 is the latest generation of subway trains introduced by HOCHBAHN in Hamburg. Designed for modern efficiency, safety, and comfort, the DT5 brings significant upgrades over its predecessors. The train's stainless steel body eliminates the need for external painting and sits on advanced air-suspended bogies, which offer smoother rides. It is a three-part train, 39.6 meters long, capable of being linked into 3 train sets, a feature carried over from earlier models. The DT5's interior is spacious and functional, with designated areas for bicycles, strollers, wheelchairs, and luggage. These spaces are created by replacing a block of seats with folding ones. Longitudinal seating has also been reintroduced, enhancing passenger comfort. Equipped with modern amenities like advanced passenger information systems, video surveillance, emergency call devices, and air conditioning, the DT5 provides a higher level of service. Notably, automatic doors reduce energy consumption by maintaining the internal temperature when passengers are not boarding or alighting. Environmental considerations play a key role in the DT5's design. It is made from 95% recyclable materials, and its braking system feeds energy back into the grid. The trains are quieter, with specially designed noise absorbers on the wheels. Additionally, the electric motor is water-cooled, and software updates now enable quiet braking with the electric brakes, resolving noise complaints from earlier models. The DT5's sleek design, created by Tricon Design, pays homage to previous models, blending modern aesthetics with familiar features. In aluminothermic thermite welding, the preheating flame plays a crucial role in preparing the rail ends for welding by ensuring they reach the necessary temperature to allow proper fusion of the molten steel with the rails. The preheating flame is typically produced using a combination of gases, such as oxygen, propane, oxygen acetylene, or even compressed air and gasoline, depending on the equipment used and the welding process being followed. The neutral flame is the ideal flame type for preheating, as it provides a balanced mix of oxygen and fuel, creating a stable and efficient heat source without excess oxygen or fuel, which could otherwise damage the material. The torch is precisely adjusted to ensure that both rail ends are heated uniformly across their entire cross sections, typically to a temperature range of 900 to 1000 degrees Celsius. This temperature is often verified visually by the appearance of a yellow-red glow on the rail ends. Proper preheating ensures the elimination of moisture and thermal expansion in the rail material, reducing the risk of cold welds, cracks, or internal stresses. The preheating duration, flame length, and gas pressure settings are defined in the welding code of practice to ensure optimal heating, which is essential for a high-quality, defect-free weld. Positioning of the preheating torch is a critical step in aluminothermic thermite welding, as it ensures uniform heating of the rail ends to achieve an effective weld. The accuracy of torch placement directly impacts the temperature distribution across the rail sections, which in turn affects the quality of the weld and the long-term performance of the joint. To begin with, the preheating torch is set in a burner saddle, which is attached to a clamping device mounted on the rail. The clamping device ensures that the torch remains securely positioned without any movement during preheating. The correct torch height is adjusted using a setting gauge, which helps in determining the proper distance between the torch nozzle and the rail surface. This distance is crucial to ensure that the flame adequately covers both rail ends and heats them uniformly. Once the torch is clamped, it must be positioned centrally over the welding gap, ensuring the flame heats both rail ends equally. The torch should be perpendicular to the rail axis, meaning it should be at a right angle to the rail's cross-section and aligned parallel to the rails themselves. This prevents uneven heating, which can lead to weak welds or defects. The alignment must cover the entire cross-section of the rail, including the foot, web, and head. For optimal performance, the flame's inner cones should be equally distributed over the rail ends. In practice, both rail ends should be heated uniformly across their width and height. Any slight misalignment can lead to improper heating, which can result in incomplete fusion of the weld or internal stresses in the rail joint. Closing of the torch is a crucial step in aluminothermic welding to ensure safety and maintain proper equipment functionality. After the preheating process is completed, the torch needs to be shut off in a specific sequence to prevent backfires, flashbacks, or damage to the torch. To safely close the torch, the valves controlling the gas flow must be turned off in the correct order. First, the combustion valve, the fuel gas valve, typically propane or acetylene, is closed. This immediately cuts off the supply of fuel to the flame, extinguishing it. After the flame is extinguished, the oxygen valve is then closed. Closing the oxygen valve last prevents any risk of backflow of gases into the torch, which can cause a flashback, a dangerous situation where the flame travels back into the torch or gas lines. The process must be done quickly and efficiently to avoid any lingering gas buildup or improper pressure balance. Additionally, the flashback arresters in the gas lines ensure further safety by preventing flames from traveling backward into the hoses. The finish of preheating is a critical moment in aluminothermic welding, signaling that the rail ends have reached the appropriate temperature for welding. Typically, preheating is deemed complete when the rail sections exhibit a yellow-red glow, indicating temperatures between 900 and 1000 degrees Celsius. This uniform heating is essential for ensuring proper fusion during the weld. Once the desired temperature is achieved, the preheating torch is carefully removed to prevent rapid cooling, allowing the welding process to commence without delay. Surface cleaning is an essential preparatory step in the aluminothermic welding process, ensuring optimal bonding between the rail ends. Before welding can commence, it is crucial to remove any contaminants that might hinder the quality of the weld. This includes rust, dirt, grease, and any remnants of old paint or coatings that may be present on the surface of the rails. The cleaning process typically begins with a thorough inspection of the rail surfaces. Any visible rust or loose material should be addressed first, often using mechanical tools such as wire brushes, grinders, or sandblasters to effectively eliminate these impurities. For finer cleaning, abrasive pads or solvents may be employed to ensure that the surfaces are free from any lingering residue. After mechanical cleaning, the surfaces should be wiped down with a suitable solvent to remove any oils or grease that could interfere with the weld. It is essential to ensure that both the rail heads and feet are cleaned thoroughly, as any imperfections or contaminants can lead to weak welds or defects. Grinding off the residual welding material is a vital step in the final stages of aluminothermic welding, ensuring a smooth and safe rail surface for train operations. After the weld has cooled and solidified, excess material, often referred to as weld risers or flash, can protrude from the rail's surface. Using a hydraulic grinder or angle grinder, operators carefully remove these irregularities, restoring the rail profile to its original dimensions. This grinding process not only enhances the aesthetic appearance of the rail, but also ensures a smooth transition for rolling stock, reducing wear on wheels and track. Adhering to specified tolerances is crucial to maintaining safety and functionality in rail operations. TECSA system of high-speed railway track mounting. A revolutionary advancement in rail infrastructure, the TECSA system of high-speed railway track mounting represents a transformative leap in railway construction, developed by TECSA since 2006. As high-speed rail, HSR has emerged as a vital component in modern transportation. The TECSA system has established itself as the standard for track mounting, due to its innovative approach, which enhances precision and efficiency in construction. The need for innovation in high-speed rail, the modernization of transport systems, demands maximum precision and technical capacity. To achieve this, there is an ongoing need for innovation aimed at improving quality while minimizing construction time. The TECSA system addresses these challenges by offering high-performance track mounting solutions that significantly enhance the efficiency of rail infrastructure projects. By integrating innovative technologies, the TECSA system facilitates the completion of high-quality projects within considerably shorter timeframes. Since its inception, the system has revolutionized traditional track mounting processes by utilizing advanced techniques that optimize workflow and reduce the necessity for additional, costly steps. Key features of the TECSA system. The TECSA system comprises two distinct and innovative methods of track mounting. The first involves utilizing an unloading track gate positioned directly on the railway sleepers. This allows for the seamless unloading of rail components directly onto the site, which is a significant departure from traditional methods that often require auxiliary tracks and manual handling. The process of assembling a track using the TECSA system involves three fundamental steps common to both methods. Topography setting. This includes the alignment of secondary network landmarks, installation of a rod, and identification of saddle points. Distribution of railway sleepers. Sleepers are strategically placed along both sides of the platform. Extension of the bottom. Following the distribution of sleepers, the mounting of the track components begins. After completing these steps, the TECSA system distinguishes itself from traditional methods. The traditional system typically requires the construction of an auxiliary track made from second-hand materials, which can be both time-consuming and costly due to dwindling availability of such materials. Efficiency and performance improvements, in contrast to traditional systems, which necessitate the construction of extensive auxiliary tracks, the TECSA system enables the immediate positioning of sleepers on both railway tracks. This innovative approach yields remarkable production results, allowing for the mounting of 1,000 meters of sleepers and extending the bottom by 1,500 meters in record time. Traditional methods, reliant on auxiliary track setups, often struggle with inefficiencies and delays. The TECSA system streamlines the entire process, allowing for continuous operation. Once the bottom is laid, the system can simultaneously start positioning sleepers on both sides, facilitating quicker assembly. This method has proven to be significantly more effective, achieving up to 266% efficiency improvement on the leading track and an astounding 400% on the parallel track. Real-world applications. TECSA has successfully implemented its innovative track mounting systems in various high-speed rail projects across Spain. Notable projects include the high-speed line connecting Madrid to Zaragoza and Barcelona, along with the railway access to northern and northwestern regions of Spain. The adaptability and efficiency of the TECSA system have made it a preferred choice for railway constructors seeking to enhance their project delivery timelines and quality. The first implementation of the TECSA system was in the Olera-Sanjun section, showcasing its effectiveness in real-world conditions. Following this, the second system was introduced in the high-speed railway line to La Mancha, demonstrating the versatility and applicability of the TECSA system across diverse geographical and operational contexts. The VDE 8.2 new railway line is a key section of the German Unity Transport Project, Number 8, VDE 8, specifically focusing on the high-speed connection between Erfurt and Leipzig, Halle. The project, which is part of Germany's extensive efforts to modernize its railway infrastructure, aims to significantly reduce travel times and enhance transportation efficiency across the region. One of the critical components of this project is the switch installation at the Grober Railway Hub in Saalekreis, a strategic point where different rail services services intersect and play a crucial role in the larger network. The overall goal of VDE 8.2 is to facilitate high-speed rail travel, enabling trains to reach up to 300 kilometers per hour on newly constructed sections. This significantly improves the travel experience for passengers, particularly on long-distance routes like Berlin-Munich. The success of this project represents a major milestone in creating a competitive alternative to road and air travel, bringing passengers from city center to city center in record time. The Grover Railway Hub is a vital node in this system, serving both passenger and freight traffic. The switch installation at this hub is crucial for ensuring smooth transitions between high-speed passenger trains and slower freight services. While passenger and freight trains have differing requirements for track design, such as minimal curves for high-speed trains and low inclines for freight trains, the Grover's hub accommodates both. To manage the differing speeds of these trains, passing stations are built every 20 kilometers along the line, allowing slower trains to move aside so that faster ones can overtake them seamlessly. Grover's also acts as a key freight junction. From this point, freight trains are directed to important logistics hubs, the container terminal in Leipzig and the air cargo terminal. This helps to divert freight traffic away from busier passenger routes, reducing congestion and ensuring smoother operations for both types of services. The broader VDE 8.2 project, which includes upgrades and new constructions along the Erfurt-Leipzig-Halle line, is part of a larger vision to modernize Germany's railway system. This involves not only high-speed travel, but also improvements to regional connections. Hubs like Grover's are being restructured to enhance transitions between high-speed and regional services, offering passengers more efficient transfer options and reducing overall travel times. Ultimately, the switch installation at Grover's and other improvements along the VDE 8.2 line are part of Germany's commitment to building a more integrated, modern railway system that serves both passenger and freight needs while linking key cities and regions across the country and beyond. One of the first key stages of the project was the track slew at Gowerton. A track slew refers to the lateral repositioning of railway tracks. In this case, the realignment was necessary to accommodate the additional track that was being laid for the redoubling. At Gowerton, engineers were tasked with moving the existing single line to a new position in preparation for the installation of the second track. This was a highly technical process, requiring planning and coordination to ensure that the realigned track was set precisely according to specifications. The slew had to be performed with minimal disruption to the operational rail services. It also involved the careful adjustment of track geometry, ensuring the realignment allowed for smooth and safe train operations. This stage was particularly challenging due to the presence of existing infrastructure, including signaling equipment, platforms, and trackside facilities. The work had to be done within tight timeframes to reduce the impact on railway services. The Rosig Rail Bridge replacement was one of the most significant and logistically complex aspects of the project. The existing bridge was outdated and unable to support the increased traffic or the weight requirements of modern railway standards. Therefore, it needed to be replaced to accommodate the new dual-track system. The old bridge was demolished, and a new, stronger bridge was constructed in its place. Another important stage in the redoubling was the removal of the 936 points. In railway terms, points, also known as switches, are mechanical installations that allow trains to change from one track to another. The 936 points were located in a strategic part of the rail network, but were no longer necessary for the new dual-track configuration. The removal of these points was essential for simplifying track layout and reducing maintenance. The points removal was a delicate task, as it involved dismantling complex mechanical and electrical systems that had been in place for years. After the points were removed, the track bed was realigned, and new continuous track was laid in its place. This improvement also helped reduce the risk of points failure, which is one of the leading causes of delays on the rail network. At Lahore, another critical section of the track was slewed, similar to the process at Gowerton. The Lahore track slew involved repositioning the existing single track to make room for the new dual track system. Lahore was a particularly challenging location due to the narrowness of the rail corridor and the surrounding geography. The slew was carried out in phases to ensure that the track could remain operational while the work was being completed. This meant coordinating the movement of trains with the construction crews to avoid any safety issues. The Lahore track slew required precise engineering, as the new track alignment needed to accommodate the curvature and gradient of the terrain. As with the Gowerton slew, this work also involved ensuring that the track geometry met stringent safety standards and that it could support modern rail traffic at higher speeds. The final stage in the redoubling project was the removal of the 935 points. Like the 936 points, these were no longer necessary once the dual track system was in place. The removal of the 935 points simplified the track layout, reducing maintenance requirements and the potential for operational failures. This removal also marked the final step in the transformation of the South Wales Railway stretch between Swansea and Llanelli, bringing the line up to modern standards and improving the overall efficiency of the network. With the points removed, the railway could operate more smoothly, with fewer delays and greater capacity for trains.